Welcome to AI for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good afternoon, good morning, good evening. Welcome everyone back to our AI for Good Discovery series on climate science. This week I'm delighted to introduce a good colleague of mine, Dr. Will Chapman, a professor at the University of Colorado Boulder. I'm excited to hear his latest research around climate model emulation. He led the recent very popular CAMulator work, and so I'm excited to hear the latest developments in that space. Over to you, Will.
Awesome. Thanks so much. I'll pull up my screen here and share my slides. All right. Oh, and now. All right. Are you folks seeing that?
Looks good.
Awesome. Well, first off, I want to say thanks so much to Duncan and Tom for hosting me, and I'm so excited to participate in this event. Today, we're going to be talking about, titled the talk, Towards Coupled Data-Driven Earth System Prediction, sort of the progress we've made working in conjunction with a big team towards doing some coupled Earth emulation with data-driven models. I want to point out that though now I'm at CU Boulder here in the Atmospheric and Oceanic Sciences Department. This is a big team effort, including members of the M² Lines team, which is a Schmidt Sciences funded project, as well as the US NSF, National Center for Atmospheric Research. And I've pointed out some people who have majorly helped with this project and the things that we've been doing here. So for an introduction, I want to give kind of a broad scale overview, and then we're going to zoom into our discussion around emulation of the Earth system, especially when we're doing these long autoregressive rollouts. But I'll frame this up sort of with a conversation around numerical weather prediction. So really, advances in numerical weather prediction or how we forecast the weather, and also climate simulations have resulted from a steady accumulation of scientific knowledge and technological advances over many, many years. And this impact has really been among the greatest of any innovation in the physical sciences. It is helping to protect human life, to drive industry, and it's something that the climate science and weather science community can really hang their hat on, be really proud of. And due to all of this kind of extremely hard work, we have slowly gotten better at predicting the weather. So this is a figure by Bauer et al. In 2015. Showing the ECMWF forecast scale in both the Northern Hemisphere and the Southern Hemisphere. And I'm sure this picture has been shown a lot of times on this seminar series, but essentially what it shows is that at multiple lead times, we're getting much, much better at predicting the weather. As we develop our models, we can slowly predict both the Northern Hemisphere and Southern Hemisphere weather with much more skill. But as a computational problem, the Earth system prediction is amongst the most intensive available to us. And what has led to this better improvement is better understanding of our physics, and really a better physics-based forecast requires majorly improving our models. The issue with this is it's really difficult to discover. It takes a lot of knowledge development to discover those new physics, but then also encoding them into some sort of numerical weather prediction system is a major developmental task, and this has dominantly happened in Fortran models that are run on really large HPC. So increases in resolution or number of ensembles is often computationally prohibitive, and we believe that this would help to improve these spaces. So in the past few years, really the past 10 or so, machine learning methods are really being deployed to accelerate the revolution of numerical weather prediction and also now climate prediction to help overcome some of these limits. And when I think about machine learning in this space, I think about a few categories, but around predictability and prediction, these are the four categories that I kind of bin them into. So typically there is post-model run, or like model output statistics, and this is a figure by my colleague Wayman Hugh showing improved precipitation run using some machine learning methods. There's some nice work around scientific discovery, and I'll point to these papers will all be linked at the end, but to some work by my colleague Antonius Mamalakis that we recently put out here looking at improving some of our XAI methods. Previously, before I started working on model emulation, I was sort of sitting in the hybrid modeling space. And hybrid modeling is when we're taking these process-based models and we're also kind of plugging in components of our machine learning-based system or machine learning systems to help improve some of the simulation or representations here. And for example, we've done model state correction using data simulation increments to kind of train off and learn some representative physical model error. But where we're going to be focusing today is really on model component replacement. So this is a simulation from my model built out of the NSF NCAR credit system called CAMulator. And as you can see, this is low-level water vapor in the atmosphere as it fluxes throughout a year in a stable simulation that runs and represents some sort of background state of a model that it's learned from. In this case, it's the community atmosphere model. So weather emulation has really come a long way in the past few years. So typically and previously, weather modeling has been dominated by large government agencies such as the US NWS, or the UK Met Office, or ECMWF. And it's happened on really, really large compute. It has taken a giant community effort with a lot of data and staff in order to prove these things. But over the last few years, there's been an explosion of what are known as AI emulators. So we can take the ERA 5, for example, which is the reanalysis data set representing our best guess of the current atmosphere state. You then train an autoregressive machine learning model at varying complexity to emulate that state. And what they've shown over the years is that these models have gotten better and better, and now the state-of-the-art models are competing with the ECMWF IFS system. So really, our most state-of-the-art weather predictions are coming both from our process-based models, but also machine learning models that have been trained off of some of the observations out of these models, observations blended with these models. So in the last 5 years, advances in data sets and machine learning model architectures, and particularly GPUs that can now hold a large portion of the atmosphere on them, have sparked a new revolution, building fully AI weather prediction. However, today we're going to be focusing more on the longer time scale. So we're now targeting the attractor of the system, as we say. So in weather, we have this initial value problem. So the emulators you just saw are optimized for trajectory accuracy. And the rate target is like 5-day forecasts. And this is sensitive dependence on the initial conditions of some layout and off horizon. So typically with limits up to 10 to 14 days, we can predict the atmosphere. However, what we're trying to do here is emulate some more of the climate statistics. So what we really want is to reproduce some invariant measure of the attractor itself. So some probability or some distribution space. And this is a fundamentally different optimization target. We're hoping that eventually we'll get to the place where we can force these models with some sort of aerosol forcing and measure some shift in this attractor. And really, to do this, you can't just take those state-of-the-art weather models and run them out for hundreds of years. You have to kind of develop a larger system for this. So model scale is assessed via kind of climatological means, variances, and spectra and tail statistics, all the things that we're using our large scale, say, CMIP suite climate models for. It's not just pointwise trajectory agreement. And something that I realized doing some of the hybrid model development and also sitting at NSF NCAR for so many years is that these process-based weather and climate models, really, process comes from iteration and development. And that iteration and development is really kind of constrained by how fast we can truly run our simulation cost. So our current suite of process-based models are slow to test and calibrate because they run on these big HPC systems. And thus they're kind of slow to evolve. And this is not a knock on those communities at all. It's a massive code base that runs on a huge HPC. So this speed of development cycles really scales with this speed of simulation. And one big advantage that we can potentially have with a machine learning based system is really fast emulation. And thus really fast development. We can kind of iterate multiple times quickly, try things really quickly and see what is actually working. So the rate at which we can improve our understanding of the climate weather system is really bottlenecked by how fast we can run our simulation. So we're hoping that if we can create good emulators, we can also feed back into the process-based models. So there's been a lot of work in the climate community, and I want to highlight a couple projects that are using machine learning. This has been no means an exhaustive list, but some of my favorite projects include the neural GCM out of the Google group. So in this case, they encoded a differentiable dicore, so they do carry sort of the fundamental equation of motion on a rotating sphere. However, for the subgrid physics, they're learning a neural network that represents these tendencies here. And this can be optimized end-to-end. It's really amazing achievement. Another project is out of the NVIDIA group, which is called Climate in a Bottle or C-Bottle. And fundamentally kind of a different perspective on how you can emulate a climate model in which they're really just trying to emulate a distribution conditioned on some future state. So they take a diffusion model and they develop these probabilistic based suites. And finally, a really impressive piece of work that has come out recently is this Samudra ACE model, which is a collaboration between the M² Lines group and the Allen Institute, in which they've coupled a AI emulated ocean with an AI emulated atmosphere and also emulating some of the cryosphere systems. And what they showed is they can have this really nice stable simulation representing here on the right is a El Nino Southern Oscillation simulation from their Samudra ACE versus the CM4 climate-based process model, and showed they were really successful at doing this. So unbelievable achievements here. And what we wanted to do at NSF NCAR was to create a platform for folks to really test and run and train these models and accelerate the speed of deployment of these systems. So what we have done is created our credit platform. So I know DJ was on this series, so DJ Gagnon was on this series recently and talked about it, so I won't spend too long on this, but what is credit? Credit is our one-stop shop for Earth system or autoregressive emulation. So it's an open source foundational research platform for developing autoregressive emulation of AI models. So really what this enables users to do is host, load, and train large data sets at scale on a large scale HPC. We run and support this on our Derecho system. It allows you to train customizable AI models at scale and deploy models for forecasting, hindcasting, and some projection-based work, depending on what has been posted. And really, we separated, we wanted to make a hyper-modular platform in which you can have different data stores. And right now we support multiple data sets, but really anything you can package into a ZAR store, we can support. Right now we host the ERA5, we host some community atmosphere model and CSM runs, as well as a high resolution reanalysis data set over the US and the GAPS forecast model. And you can also load multiple model platforms. So we have multiple hosted models. Our flagship model is the WEXFormer, which we'll be talking about mostly, but we have a suite of different models that you can then load. It's a hypermodular system, all called with a simple name list. We then wanted model agnostic physical constraints. So is there a way we can then constrain some of the Earth system budgets that we know are important that you can simply turn on and off and ensure this is constrained? And then a large suite of processing frameworks in which you can create ensembles, do vertical interpolation or gridding. And this is all hosted on the system. And we know that there are competing platforms out there, for example, like the ECMWF and MOI. But our philosophy here is that we're trying to create something that is maximally usable for the users of our community, and can be maximally integrated with. So you can really get your hands on all kinds of components of the credit system in order to swap out and trade these things. We're not kind of put into one category of different data or model or anything like that. As long as you can host it within this, you can run it at scale. And we handle a lot of the sort of pain points from building a model platform development for you. And with this, we've released a series of papers all around this platform. And I think it's an exciting suite of development sort of in the AI. This is all on the NWP side. So our first paper out was introducing the platform, and then we have a suite of other papers. So I want to briefly go into these before we're getting into the CAMulator stuff. But most of this is built off of our WEX-former backbone. So this is a model that we originally developed, and it's sort of a hybrid architecture. It's a cross-former encoder and a convolutional decoder. It takes the form of a UNet that has transformer blocks on the up and down, sort of loops of this encoding some scales of the atmosphere as it goes across. It has these cross-embedding layers. So essentially, it's taking multiple convolutions from different scales in order to understand not only large-scale connections in the atmosphere, but some of the mesoscale systems too. It then has these long, short attention layers, meaning that it's attending things right next to sort of in neighboring grid boxes, but is also attending more on the global scale. And what we've shown is it's really good for autoregressive forecasts, handles variable input sizes through dynamic positional embedding, and it's really designed for efficient global weather prediction. So WEX-former really combines this transformer scalability with a CNN reconstruction, really for an efficient forecasting. And the first thing we did is we showed that, we had to prove that this model was worth its salt. So here's a figure showing 2-meter temperature and geopotential height. We've got the IFS model at 6 hours, as well as some other state-of-the-art models at the time. And what this figure essentially shows is that our WEX-former model is outcompeting or competing with both the IFS and some of these other state-of-the-art models. So our first goal was kind of a tick mark to prove that we could have this platform to do this. So the next thing that we're kind of working on is injecting some of these stochastic layers inside it. In order to do ensemble forecasting, we needed to control certain layers of ensemble spread. And what John showed in a research paper, or a recent paper, is that using this UNet architecture, if you inject noise at certain scales in intelligible ways, you could then control exactly where on our spectra we are injecting spread into the model. So for example, if you're at this really lowest scale, you can kind of control a broad scale of structure, but if you go out to the more finer scales, this will control some of the finer scale of the atmospheric variability, and we can alternately tune these things. But what's most relevant for our long timescale prediction is a paper led by my colleague Kyle Shaw, in which we are combining our weather prediction with some conservation schemes within credit itself. So what we showed is that you can take the credit model, run it forward in time, and then what we are known as post blocks afterwards. So the credit model runs, we then correct for any non-negative fields, so any fields that have gone negative that we know shouldn't be, we correct for those. And then if you apply these systems in the right order, first fixing global dry air mass, then global moisture, and then total atmospheric energy, we show that you can fully constrain this system. And we do this with simple multiplicative corrections to the atmosphere. So we compute a residual and then make a correction for it. And what he showed in this paper is that a model without these constraints will tend to drift. This is the global dry air mass. But if you activate these constraints, you can see that it holds steady for long periods of time. And the reason we have a little bit of a wiggle here is we're using float 32 precision. If we up that to float 64, you kind of knock that down, that residual down to 0. And what you can see is that the residual there is quite low. So you can constrain these systems with our post blocks, and all you do is turn them on and off. We do this both during training and during inference, and we showed that this was very important to also train with these systems on, and I'll show you another result that kind of proves that. But on the weather timescales, what we can show very simply is that by turning on these post blocks, you can improve your weather predictions. So particularly at the longer timescales, so past about 96 hours, you can see this yellow line is below the red line. And essentially what that is saying is that our skill scores are getting better for, in this case, 500 hectopascal temperature, geopotential height, and mean sea level pressure. So training with the correct physics in the model seems to improve this. And what was sort of also exciting for us is that we were able to run these long timescale simulations. So we could take a 6-hour forecast and run it for a year in time and show that a model without these physical constraints will sort of drift in time, and going back and forth with some sort of seasonal cycle here. Whereas our model that has the physics constraint turned on can be exactly conserved. And the way, when I say conserved, I mean whatever is the field that the initial state is sort of held forward in time. So what this really made us excited to do was start to work on these long time scale predictions. And this is where we kind of get into what we are doing here now. So this is CAMulator V1, in which the goal was to produce a stable and fast AI emulator that reproduces the statistics of the community atmosphere model, so state-of-the-art atmosphere model, given some set of forcing variables. So the atmosphere is the costliest component of CSM, or our community Earth system model. So it would be really beneficial if we could somehow speed up development here. So this becomes a development and inference bottleneck. And if we can emulate trajectories with high fidelity, we could potentially increase, for example, our uncertainty estimates by running multiple ensembles. So what we did is we took this model, made some adjustments to it, and out popped CAMulator, which is an emulator of the CAM model, which is, I developed it, so I got to name it, and now people have to go around using the word CAMulator. So we are currently developing a whole bunch of other Earth system component models. And this is showing a long autoregressive rollout. Again, that specific humidity field at the lowest model level. You can see nice atmospheric rivers, some pulsing in the tropics that we should be seeing on the diurnal cycle. And overall, beautiful simulation of our system model. So the first thing I want to put out up front is CAMulator is a research model and should not be used for operational climate projection at this time. So big disclaimer, if you pull this thing off the shelf, it is only emulating one trajectory of our community atmosphere model. And I'll show you some of the limitations of it there. So CAMulator's backbone is using this WEX former, but with some adjustments to it. So a few things that we had to adjust is taking our convolutional 2D layers and sort of our upsampling box and replacing those with pixel shuffles. And a pixel shuffle is a really neat algorithm in which you are producing convolutional kernels and then sort of reshuffling those to create an upscaled picture of this. And what we found is that the convolutional 2D, given sort of the sweep of the models and the size of those kernels, created some grid artifacts. So the pixel shuffle then fixed this. The second thing that we did was added some residual sharpening blocks. So this is simply a residual layer that has a sharpening convolutional neural network that passes over. It doesn't change the size, but just helps to improve the resolution of the model. So with these two changes, we were able to then emulate the community atmosphere model. And we've done this sort of in two suites so far. So we have two simulations that we were really first trying to emulate. So the first one was this CAM6 AMIP simulation, so a forced atmosphere simulation that ran from 1979 to 2015. You pass it through the credit platform, and then you get this CAMulator branch. And in a second suite, in which we're calling CAMulator V2, we then take this model and learn a coupled simulation. So this is from CSM 2.1.5, which is our IPCC submission to CMIP suite, 6th suite. And we ran this from 1979 to 2050. And there was a train test split, so we actually trained through 2012. And then I'll show you how this kind of projects out into the future. And to move from CAMulator V1 to V2, we just did a simple fine-tuning and took, again, this community atmosphere model, which now runs on this 1-degree resolution, ran it from 1979 to 2015, trained here, and in our V2, simply fine-tuned on the second model. Loading up some weights, we did change a couple fields, so is a bit of an aggressive fine-tuning. And what are we actually emulating? So we have a suite of different variables within CAMulator. We have input variables that are static forcing, so the geopotential height representing the surface, a land sea mask. And then we have some dynamic forcing variables, so the incoming solar radiation atop the atmosphere, and then at the surface is the sea surface temperature. We then have prognostic variables, which are variables that go into the model and then are out of the model too, so sort of fed in this autoregressive manner. And then we have diagnostic variables. So precipitation, some cloud fields, surface stresses, and then a bunch of flux fields, so we can ensure that we are preserving the fields in our conservation blocks. And these are just diagnostic fields, so they're taken from the output and only diagnose, but don't go back into the model. And in V2, all we did was we added some CO2 forcing, so the CO2 volume mixing ratio, and it's also forced with the ice fraction from our SICE model out of NSF NCAR. So one thing that I will criticize us on is that we are not doing the most elegant treatment of the spherical geometry of the Earth. But the way that we solve this is we simply pad the boundaries. So we have these periodic boundary conditions in the east-west, and then in the north-south, we flip the pole and then reverse it by 180. And this way, things that move across this pole, we can still do these convolutional layers. And then our prediction is just sort of cut out from the middle of this value. We're currently porting in things like the HealPix grid, so we can start to do this a little bit better within our credit system. But in the meantime, this seems to work really well for us, though it is not really treating the geometry of the Earth well. We tend to adjust for area latitude weighting via some cosine function. So the first interesting result that we saw is when we were training CAMulator, what you do is you first train without the post blocks turned on. And in the first 20 steps, we did that. So this is a consistent result whenever we start from cold. You have your classic training curve. We're using mean squared error to train this. I'm then validating. So this is the validation MAE. And we're running this out to 14 days on all of our validation step, because what we found is that we needed those long stable rollouts in order to have a validated state that could remain stable. So the first cool thing that we found is that when we turn on this physics constraints, immediately we see this improvement in our validation MAE. And this is consistent with the results we saw on the NWP side, but it was really nice to see in our training run too. So as soon as you turn on these training physics, the next time step, you're representing the system much better. What we then do is take another time, we optimize on 2 time steps in total, and our final model is actually, so you can imagine the error jumped up here because we're now making a 12-hour prediction instead of a 6-hour prediction here. We train this out in time for a multiple periods, and then we grab one of these points and we validate the model as it moves forward in time. The way that we actually do our model selection is we do long 10-year rollouts and we look at the representation of the attractor itself. And I think this is really interesting because what ends up is we don't actually have the best weather prediction model. So our time scale, our short numerical weather prediction with CAMulator is not amazing, but it does represent the lower frequency statistically better. So there's a fundamental sort of mismatch between those two states. And really, we are optimizing on the weather timescales, but we're hoping that it represents the longer timescales. And this is not an uncommon feature. So this is from a paper by Carl Bauer that came out a few years ago when they were introducing their HealPix mesh. And what it showed is it's looking at zonal 3-day mean Z500 height as a function of time as you move forward. And most of these state-of-the-art weather models, if you run them forward in time, though they're really good at predicting the weather, sort of misrepresent the low frequency variability there. So fundamental mismatch there, and I think ACE2 will say the same thing. But the real speed up is that on one NVIDIA A100 GPU, we can get 480 simulations per year. So this is roughly a 350 times speed up of the host model given similar computational constraints. But in practice, you typically run the host model on 10 CPUs. So it's about 14 simulation years per day. So we can see is a dramatic improvement. And just to show some quick results with CAMulator is that we are able to achieve these long stable rollouts. If we force it with observed SSTs, we get a nice distribution of spread. And here, this is the integrated heat as we move forward in time. Purple shows CAM, and then That's 15 runs of CAMulator, all done in a single day, that represent this sort of trend in the integrated heat content. But if we force it with climatological SSTs, it remains stable for this whole time, so we can run long integrations. The diurnal or the seasonal cycle and diurnal cycle look really good within CAMulator. So here's the 2 meter temperature, stable rollouts for long periods. There are slight amplitude differences, but a lot of these can be accounted for by internal variability of the system. And if you look at the biases themselves, they're quite low. So what I'm showing here is the mean precipitation on the left with the sort of bias down here. You can see values are fairly low. This is for precipitation, 2 meter temperature, and wind, the lowest levels. And you can see the magnitude about 1 or 2 meters per second here, 1 or 2 degrees Kelvin, and low precipitation biases. Another thing that we observed is that the large scale modes of variability within CAM6 are all within CAM6 model spread. And they represent this variability really, really well. So this is on the left panel showing 2 representations of the Pacific North American pattern, which represents about 38 to 40% of North Pacific variability. You can see that the patterns are well represented within both CAMulator in terms of and CAM. And then we have the North Atlantic oscillation on the right. And again, all of these values are within 30-year model spreads of our right. So the explained variables are comparable and the emergent dynamics are preserved. So finally, some interesting results is that it's representing El Nino Southern Oscillation well. So I'm showing a regression of the precipitation in CAM on the left and CAMulator on the right. These have about 0.93 pattern agreement. So it's slightly muted in the Pacific, but overall a good representation. And interesting, the extremes are still within the model. We show some biases, and I'll show those here in a second. So this is the maximum 2 meter temperature per year in CAMulator on the left and CAM on the bottom, and then the maximum 6-hour precipitation values on the left and right. And we definitely see some disagreement. So a few degrees in maximum difference of the 2 meter temperatures. However, there are representations where CAM is actually stronger than CAMulator, so we're not muting them entirely, but sometimes they're represented wrong. And our differences of extreme precipitation here shown on the right, you can see especially in these TC regions, typically we're over-predicting the precipitation, we're under-predicting a little bit at the mid-tropics. And finally, the precipitation distributions themselves actually look quite good. The one thing that we're noticing is that we have less of a drizzle problem within CAMulator itself. So here's the rain rate, and typically CAM tends to have high drizzle periods, and CAMulator seems to mute those, and we know why. It comes from our physical constraints of water conservation here. So this is an unintended benefit, but is not representing the host model exactly well. And then if you push these things out into the future, so we've, again, trained on 1979 to 2012, but then if we force it with ocean conditions from 2015 to 2050, again, this is total column heat, you can see that it tracks the host model, which is CAM, really, really well. So it seems to generalize to a little bit of warmer climates. But potentially a more interesting generalization comes from, provided by Stenny van Loon, who is at CSU, and he did what are known as patch experiments on CAMulator itself to look at some idealized response. And you can really develop using, you feed the model climatological sea surface temperatures, and then you force it with some 2K increased or 2 Kelvin increased patches. And you see, look at the linearized response of these things. So there's an idealized response, and you can also develop these large perturbation sensitivities if you run these patches globally. So this is a powerful sort of out-of-sample diagnostic, and it evaluates emulator skill in an idealized and controlled setting. It helps to probe this out-of-system behavior. And really what we want to see is, does it behave like the host model? And conveniently, Margaret Duffy ran some, and colleagues ran some nice experiments on CAM6 using the same framework, so we can make direct comparisons to these things. So the first nice result, if you force these patches over the maritime continent, what you get is this nice Rossby wave response that we would expect. And it actually looks quite good compared to CAMulator. So tropical heating source develops these nice Rossby waves. Then you can go and do a huge patch level experiment and develop what are known as these sensitivity maps here. So for example, each patch gives a finite different estimate of this response, and this is some sort of weighted combination of some sensitivity to this surface temperature. So you can interpret this as a numerical derivative or linear response to the climate system itself. And what we saw is a fairly nice result. So in CAM6, if you develop this for top of atmosphere feedback, so this is a radiation at the top of the atmosphere, you can show that in the bottom figures here, in our deep convective regions, you should have this sort of negative response. And in our low cloud deck, you should have this positive response. And while CAMulator isn't perfect, it is representing these physics semi-well. You can then take these Green's functions and use them as sort of the host model. So you can turn these patch experiments and convolve them with the observed sea surface temperatures. And what that will develop is then this linearized response of the patch estimates themselves. So what we should see, given that we have this net top of atmosphere radiation is slightly decreasing as we move forward in time. This is CAM6 patch experiments, and when we run this same experiment with CAMulator, what we can see is very clearly in the pre sort of emergence of our global warming signal, we have nice constrained variability, and then as that warming takes place, you can see that we are responding exactly the same way. So this suggests a climate response that is well approximated. So what we have done recently is we've shown that this model is now responding well, but can it be used to help develop a true coupled climate system? So we've been working significantly with an uncoupled system at this point, forced by atmosphere. So this is an interactive, however, our climate system is very interactive. So it has these air-sea feedbacks determined by significant pieces of our climate system. For example, the El Nino Southern Oscillation and the Madden-Julian Oscillation, the AMOC are all sensitive to these sort of fluxes. So what we wanted to do is we could say, here is CSM as a whole. It's composed of a bunch of host models connected by a coupler itself. Could we then take this atmosphere and sort of swap out our atmosphere, which is the process-based model, with our machine learning-based model, and see how the model responds and reacts to that? This should represent a giant computational speed up. So this is exactly what we did. So we coupled our ML atmosphere to a Fortran physics ocean. In this case, it's POP, which is the model that kind of sits underneath CAM and CSM. So CAMulator replaces what's known as a data atmosphere, and we use the coupler itself to exchange information between CAM and the ocean. So in our first results, we're seeing a pretty good speed up. So we can get about 42 simulations per day, and I'll put that in context here in a second. But the coupling machinery, what it really does is we take just a simple nameless tag and we write a couple Fortran scripts within CSM, and then we can now call this case CAMulator within our CSM framework. So why are we not doing this fully in Fortran? Well, as it turns out, there's no computational cost to just doing this with file IO. So we don't have to rely on things like ftorch or 4Pi. There's no socket feeding. And we can also stay off expensive nodes within our computational system. And all we do is we hand files back and forth. Additionally, all the physics can be handled sort of server side, as I'm calling it. So this is all handled in the Python itself. So it keeps sort of a separation between the Fortran, which not a lot of people are comfortable with, and the Python, which a lot of these model developers are. There are two adjustments we had to make to CAMulator. So we had to adjust some of the flux conversions from calculating net fields to downwelling fields. So CAMulator outputs net fluxes at the surface. And we transferred these to the downwelling fluxes by using the surface albedo for the shortwave fields. A long wave, we used a black body reconstruction. So simple server side, all handled on the Python side. We then had to do one more thing. So we needed a proper reference height for our bottom to develop wind stresses, sensible heat, and latent heat, which is all these fluxes that go in and out of the ocean. However, CAMulator uses a sigma pressure hybrid coordinate. So we had to develop sort of a dynamic representation of our bottom geometry so that the coupler could then calculate these variables themselves. So after we made those two switches, what was really nice is we showed that there is actually no computational slowdown from using a data atmosphere. In fact, we're a little faster than just feeding a data atmosphere. And I think this all has to come down to the model I/O. But we can get about 42 simulations years per day. And what this comes to is our atmosphere step is about 220 milliseconds. For reference, one 6-hour step is about 5,000 milliseconds on 8 CPU nodes. So really this represents 100 times speed up of our atmosphere. And CSM's ocean and ice compute is really the bottleneck. So this file I/O that we're doing by exchanging this is really not affecting our model runtime at all. So what we did was we then were able to do a large speed up over CAM6, which enables large ensemble experiments, parameter sensitivity sweeps, and some rapid prototyping of new coupling strategies. And what's really nice is you can do this with any server-side model now. So in Credit, all you have to do is write a simple server that exchanges these information. And now the Fortran side will never change. And you can do simple model input output. And this is all in a PR that's going into Credit here coming soon. So if you push that forward, I'll show you some initial results. So here's a simulation of our Fortran ocean on the left at monthly timescales and our monthly precipitation on the right. What we found is really, thankfully, we ran this simulation for 100 years or so and saw no major drift in the ocean. So what I'm showing is the CSM sort of forced simulation in red, and then CAMulator, which has no forcing, which has static forcing that remains constant as it goes throughout these times. This is after some amount of spit up. So the seasonal cycle remains intact. We don't see a giant mean state biases, but I'll show you some that do develop. So we did this with both ACE2 and CAMulator. So we brought ACE2 into it, and I'll show you a couple results with ACE2 too. So ACE2 seems to jump up and settle to about 2023 levels with an error of 5, but then hold very, very constant at that hole. So it maintains long-term stability in coupled setting. So there's minor drift at the beginning, but then it tracks error 5 really, really well. So it's actually behaving quite nicely. Some biases definitely do develop. We now have this new dynamic system where we have a coupled atmosphere. So I'm going to show you some bias plots here. So here's 2-meter temperature, CAMulator coupled on the left, CSM on the right. And the biases that we see develop are definitely sort of in our Arctic regions, which worried us at first, but they are stable. And they're about 1 degree difference than our host model. The thing that is really starting to worry us now, and that we're working to fix, is our precipitation field. So what we see is a shift of the South Pacific convergence zone here. And I'll show you a consequence of that. But we can start to look at some of the coupled modes which in the system, which is really exciting. So here is the some figures showing the El Nino Southern Oscillation. So here's the temporal structure of El Nino. In green, we have CSM2. In purple, we have CAMulator. And we can see these nice peaks. The distribution is represented well. This is for the Nino 3.4 anomaly within the tropics. And one thing we noticed is that what CAMulator is doing is sort of, we have a little bit too periodic behavior within our El Nino Southern Oscillation that peaks a little early. So here's the power spectrum. Years on the y-axis. So we have an El Nino Southern Oscillation that is peaking at about 2 to 3 years rather than 4, which we see in the model. However, our distribution of the actual anomalies themselves seem to be really good. So there are more extreme cold events, so there's a bit of a negative skew and a slight deviation in the tails. But overall, we are developing a stable coupled system. If you look at ACE, this is the one thing that it doesn't do particularly well, is we have a bit of a muted El Nino Southern Oscillation. So shown in this distribution on the top, you can see that most of the anomalies themselves are a little bit muted within that range. And I think when they developed ACE Sumatra, the coupled emulator model I've spoken about before, they had to do some retuning of the system. So we're excited to then take this ACE Sumatra and see if we apply that then to this system, if it would develop a more stable dynamic system. And, you know, this isn't exactly a fair benchmark for ACE2 as they were trained on a completely different dynamic system. But what you can see is that there is representation of the El Niño Southern Oscillation, and it has some of the correct structures peaking at similar times to the CAMulator. So the time series shows some reduced event magnitude and some weakened variability compared to the CAMulator system. And the spectral characteristics, while we had to normalize to show them because they're a bit muted, seem to peak at the same time as CAMulator. So the peak's a bit flatter and less distinct, but still there, definitely. So it is developing this these nice coupled modes. If you look at the actual El Niño Southern Oscillation temperature response in our coupled system, we see some noticeable differences. So particularly, we don't have as westward extended of the anomalies, which is typically considered a model bias within CAM. This is CAM on the left and CAMulator on the right. So we fixed this bias, but really what we want to be doing is emulating the system. And as a response, you can kind of see that precipitation pattern, that shift of that southern South Pacific convergence zone that we see there. So some issues to work out. However, ACE5 actually has despite having a muted El Niño, the representation of the global response, so the surface temperature response in ACE itself is actually quite good. So if we can figure out how to couple the system a little stronger and develop a stronger El Niño, it seems like it would have a really good response. So that's really nice to see compared to this Era 5. Another coupled mode that typically we struggle with in CSM, but is represented, is the Madden-Julian oscillation. So it's this convectively coupled wave in the tropics. And what you want to see is this nice propagation signal. And what we can show is both in coupled CAMulator, or coupled CAMulator really represents this mode well with spatial correlation maps of about 0.9. So this coupled system is sort of coming back and doing really, really well. Also, ACE has a really good and really strong MJO correlation. So they showed this in their uncoupled model, and this has remained within the coupled system. So compared to Era 5, it's quite good. And it seems to have this really nice propagation signal that we'd hope to see in these coupled systems. So I'm getting to the end of my time here, and I want to just offer some perspective, and we are developing these systems more to show what we can do with some of the model development here. But what I see this work as sort of a proof of concept that we can start to use these models to develop new dynamic systems, and maybe there are ways that we can leverage them. So I think in the weather prediction space, from 2020 to now, really our AI models are really starting to catch up and perform as well or better in some scenarios than our numerical weather condition models. So in 2026, we're really seeing this birth and boom of the AI weather prediction models that are doing really, really good things. They're all trained off these traditional numerical weather prediction models and observations, so it's necessary that we continue to develop these things. But our AI systems in the weather space are really, really, really well. However, in the climate modeling space, we are still lacking behind, and there's a lot of work to go. So I think component emulators are starting to show some measure of fidelity, though they're not responding to forcing in the same way that you would want them to. But the component emulators are quite good compared to some OMIP simulations or AMIP simulations, and there's a lot of science that can be done here. This work I'm calling embarrassingly hybrid models, and these are models that are, we're replacing an entire component model with. I think this is far from a true climate model yet, but it's starting to potentially aid in running some of these things forward and doing some good model development. And however, I think there is still a long way to go before we can start to compete with some of our fully coupled climate models, or even some of the models that are using machine learning based hybrid parameterizations, and thinking specifically of things like the CSM machine learning enhanced project, which is going on now, and also the CLIMA project, in which they're starting to leverage some of the data components, and they will have proper climate models by the end of this thing. So a lot of ways to go, but I think there's a lot of space here that can potentially be benefited by these hybrid versions of models. So some of the science questions that we're currently trying to tackle with this new coupled system is looking at emergent coupled feedbacks, within the system. So are those represented well? I've showed you some statistics on ENSO fidelity, but we think we can improve these all by improving sort of our optimization frameworks, and we're currently coupling to oceans that are actually more easily optimizable and faster. Looking at some compensating error diagnostics, so especially once we get ACE2 coupled really, really well, and we can develop some of those more ENSO structures, ACE2 is really representing ERA 5 well. So removing some of those biases represented by CAM and replacing them with ACE2, we'll have some interesting compensating errors that have been tuned for in the ocean. I think obviously doing some more rare event sampling and climate sensitivity works. And just from a model development perspective, we're looking at CAMulator generalization to a coupling model, coupling dynamic modes, and how we can start to do better out of distribution tests, and then hopefully impact the calibration space. Calibration is a big, big project within traditional process-based models, and if we can have a really fast component, maybe there is a way for us to start to impact that space. Again, looking at compensating error frameworks and fast coupled climate ensembles. I think we need to pay particular attention to machine learning-based stability requirements, and then really do some more detailed diagnostics. But one call out that I just want to give to the community that I think could have immediate impacts is currently, I want to harken back to this figure. We are still training on weather timescale loss functions. And I think we need to start thinking about how do we encode some of this slower mode behavior. I think we can borrow things from like the LIM community or the linear inverse model community and some of the stochastically forced ODE models. But I think it would be a good focus for kind of the next few years is to figure out how to actually start encoding some of this slow behavior rather than just validating for it. So with that, I want to thank all the folks that helped with a lot of this work, and thank you for your attention. I've placed my email here. All of this code is open source and ready to be used, so I appreciate your time and attention, and I'm excited to take any questions that you might have.
Thank you, Will. That was fantastic. I'll start with a question. I think Duncan has one as well, and then we can take the first question from the public. My question is, you mentioned aerosols. So as you develop these models, how are you hoping for them to respond consistently to worlds we've never seen, never observed, maybe that are completely outside of your training data, especially localized response to aerosols? What strategies are you thinking about?
Yeah, and I think right now the best solution people have are, and I, ignoring your question entirely, apologize, but training on different scenarios and just being able to fill out the uncertainty space and seeing if we can interpolate between those spaces would be a huge step forward. Because then we could start to just develop a lot of sort of uncertainty scenarios that kind of span the range and hopefully are faithfully responded with. So dodging your question, inside your question, I think there's some exciting work that can start to be done on especially attending to local physics. Because right now what we are doing is really serving these global maps, and I think to a lot of extent the model is memorizing a solution rather than actually representing the physics well. So the first step for me, and we have some work in my group working on this, is can we generalize better if we're working in local spaces, because then it's forced to then take this model and generalize it every space on Earth, thus it has to learn the physics. So if you start to apply that more in the aerosol frameworks, hopefully that starts to move us forward. And I think there's been an exciting group out of NCAR and Bill Collins that start to play at some of these things too. So yeah, dodged your question a little bit, but I think it's a really hard question.
Thanks for it. Was really, really nice talk. I guess actually mine's somewhat related, but maybe I'll try it at a different angle, right? So you kind of pitched these tools as a way of speeding up the development pipeline for things like CSM, right? It's like 1/over the simulation time. So if we cut the simulation time, we can hopefully improve the rate at which we get good models. How do you picture that working? So we've got a pretty good atmosphere emulator now, and you can plug that in. That was very cool. How does like an NCAR scientist now kind of use that to...
So the first way that I kind of think of it is that we have this model development framework where typically we calibrate and we develop in these uncoupled spaces. So what that does is it develops a really good ocean that responds well to kind of the fluxes that we have on from an observed atmosphere and also sort of this like perfect scenario. But it's kind of once we go and we couple these spaces again, we develop these compensating model biases. So what I see this is sort of an intermediate step. If we can represent the atmosphere and the response, and we saw that we're pretty good to some responses with Sene's work, then this offers a fast development pipeline, kind of an intermediate step for us to get to a place where we could potentially calibrate a little bit faster. So it limits the subspace of search that we have to do with our full coupled emulator. An interesting result that I didn't have time to put here because you noticed that I was going really quickly is there is a simulation in which I can adjust the albedo and I can make the Labrador sea freeze. And that has been a really, really big problem for CSM model development. And one of the issues is we want to attack that with some XAI, but we need so many simulations of the Labrador sea freezing. So if I could do that, and then we can start to develop some XAI to see some of the drivers of those things. And the fact that it was an albedo change that kind of adjusted this. Maybe it's not the only driver, but it's one. It gives us an opportunity to start to work on this, more coupled space. Another kind of paradigm moving from uncoupled to, or process-based component models to a fully coupled system.
Cool. Yeah, I like that. Thank you.
So we have 2 questions from the public. I'll start with the first one. Do you think there are fundamental reasons why AI is lagging behind in climate models as compared to weather models?
I think it's just a much harder. I'm not going to say it's a harder problem. The weather community is doing amazing things, but the optimization frameworks are kind of designed for shorter time scales. And right now, there's a limit of compute in order to like run these things out for a long, long time and start to constrain on some of the slower mode of variability. So it was a really, really good first test case was this weather prediction problem. We have a lot of really, really intelligent people starting to work in the climate space and seeing how we can start to leverage this. So I do anticipate there will be some catch up, but there is like a bit of a fundamental mismatch between what we're currently optimizing for and what we need to optimize for. And this is technological. It is a bit of just like it is a more complex problem. So we need more time to think about it and develop. So fundamentally, will machine learning be the final answer that eventually gets there? I don't know, and I don't think a lot of people know. But if we can start develop some of the frameworks to speed up some of the development, I really think more things will come. Another exciting branch that I haven't really talked about is like there are fully differentiable end-to-end process-based models now that you can optimize in different ways for, and I think that's a really exciting way to go. So again, dodging the question a bit, but yeah.
I'm seeing another question from the public about how well CAMulator simulates AMOC or related indices in the long run.
Yeah, we're investigating that a little bit more right now. There's some indications that it's doing okay. We don't see major drift so far, but we've also only run it out to about 1,000 years. So I think we need a bit more testing before I want to make anything completely, definitively stated. So let's just say results pending on some of that stuff.
Okay, now I'm gonna go back to my own questions because I'm really intrigued by your statement on extremes. I agree there's a ton of potential, right? If you run large ensembles faster. But as you train these models, and that's related to this optimization challenge you were mentioning, as you optimize them for longer and longer rollouts, aren't you implicitly smoothing them and then not being able to capture the tails and extremes as well as you would like? Or do you see that as a challenge you could solve, like a magical loss function, or fundamentally fighting objectives.
Well, I hope there's a magical loss function out there. I think another yeah, I don't think that the solution is actually just huge autoregressive long rollouts. I think it needs to be something that is more encoding some sort of emergent behavior from the slower time or from the faster time modes that then encodes some of this longer behavior. And what that is exactly, we've been thinking about, but I think there's still results pending there. But what I can also say is, like, to your question, is there is a lot of creative things that we can stick on top of the models in order to better develop the extremes. Diffusion models that sit on the output that then, spec out that extreme space, I think is one option. But I think we need to be acutely aware of the problem that you just stated, is that, like, there are reasons that we use climate models, and a lot of those reasons, especially in industry, is to spec out the extremes. And right now we're not optimizing for the extremes. So yeah, fundamental push and pull there. But I think there are probably creative ways that we can get around it. We'll just see what those ways are.
So can we hope for like a high-res downscale CAMulator soon?
Yeah, no. I think we are working on the CONUS 404 emulation right now, and I think Kyle has some exciting results on that. And then we can use that to kind of fine tune some of the high resolution stuff. So I think, yeah, the goal is to move that direction, but there are a ton of goals at this point.
I think these are exciting news and thoughts to finish on. So thank you again, Will. We were thrilled to have you today. And
Yeah, I really appreciate it.
Will.
It's so much fun.
You were great talk. Thank you. So we'll close it there. Thanks again, Will. Look forward to see how these things develop over the next months and years. We have another speaker, actually, double headers. We have another speaker on Wednesday already this week. So April 1st, we have Cara Lam talking about physically informed machine learning for cloud physical processes. So kind of at the other end of the scale. So they'll complement things nicely, I think. So join us then, same time, same place. In the meantime, thanks again, Will, and we'll see you all soon. Thanks all. Bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.